Hi, this is Group 3 from MAE201P. Here's our design review for a 100-meter tall wind turbine. Our wind turbine contains three main parts: the tower, generator, and blades. Different simulation analyses are performed to these parts. The first part is the generator. Heat will be introduced by high current flow during turbine operation, so thermal analysis is performed to study the effect of heat on the generator. For the simulation, we add heat generation at the center to simulate power loss, and the convection to all other surfaces to simulate heat dissipation. The original design is just the outside chamber, so we modify the model similar to the real generator. Here are the results. We can clearly see the steady-state temperature distribution. The original design has a high temperature on the inside coil, so we add 8 ventilation holes near the central coil. The heat dissipation is very obvious. The maximum temperature has dropped, but it still seems very high, so we try to put the holes closer to the center. It turns out that the closer the distance is between the holes and the center coil, the better results the heat dissipation is. For the static analysis of the blade, we have different input conditions. One is the pressure due to the wind drag force, the angular acceleration, and also the gravity. The material is E-class fiber, which is commonly used as wind turbine material. We have changed the design of the wind blade, so it's easier to compute the result and increase the robustness. Due to its central symmetry geometry, we can only analyze one blade and set symmetry boundary condition at the cross-section surface, and we also add the fillet at the sharp edge of the blade. We did a stationary static analysis which assumed the turbine is not working, and rotational static analysis assumed there is rotation and radial acceleration. For the stationary, we compare 3 different airspeed effects to the wind blade, and for the rotational static analysis, we set the max turbine working airspeed and add different radial acceleration. Since we want to learn the part behavior under extreme condition, the compared result is shown above. Since our generator is assumed to generate heat, so we need to know if the heat is going to affect the turbine structure. So we did a thermal analysis of the wind blade. Then input the temperature distribution for the thermostatic analysis. The high stress is mostly located at the high temperature area, which is the center shaft, so we don't need to worry about it since it's fixed to the generator. At last, the blade is going to have wind blowing from all directions, and its working conditions have all kinds of vibration. Thus, the frequency analysis is also necessary. As the result shows, the wind blade have a natural frequency of 0.5 Hz, so we need to avoid this frequency for the working environment. For the tower and base, we chose steel as our simulation material, which is widely used in the industry. Boundary conditions and fixtures are shown above. Drag force from the blade is calculated from the equation, where the wind speed is a variable that changes under different load conditions. Original model has a solid body for the tower, so we made 2 design changes for the model with 100mm and 300mm tall tower wall thickness. Static analyses are performed under different wind speeds. Corresponding maximum stress and displacement are calculated. High stress areas are located at the bottom of the tower. The overall FOS is high for both models under all wind conditions, but as we increase the wall thickness to 300mm, the displacement at the top of the tower drops significantly. The closed-form solution is different from the simulation result. This is mainly due to the different structure of the beam we analyze. We also perform buckling analysis to the tower and base since it's a tall and thin structure. As the wall thickness increased, the buckling FOS also increased. The buckling factor of safety implies that there is no risk of buckling for the structure under applied loads. In summary, for the blade, due to the sharp connection, the overall FOS is lower. You still need to change the material composition and the structure before it could be used in production. About the generator, the center temperature is still high, which mostly due to the design and boundary condition setup. At last, for the tower and base, the simulation shows a great promising for the structure robustness, so so the design is good. This is all for our design review for the wind turbine. Thank you.